evening. Happy Tuesday afternoon, and welcome to AP Live. My name is Roger Siegel, and I am working tonight, as always, with my partner, Kristen in Frisco, Texas. Hi, Kristen.
Hello, Roger, everybody. How are you guys?
And so tonight, what we're going to be doing is we're going to be moving forward with our review for our AP Physics C E&M exam, which is 2 weeks from yesterday. I'm sorry, not 4 weeks from yesterday. Sorry about that. And so not to worry. And we're going to get you ready for that. So this is going to be a wonderful night. Thanks for joining us. So tonight, we're going to be talking about potential, electric potential. And I got to tell you, you might be mad with physics teachers after tonight because there's a difference between electric potential and electric potential energy. Don't ask me why they're called so close to the same thing. They just are. And so that does confuse us somewhat, but we are going to get into it today and it should make sense to us. Once again, my name is Roger Siegel. I'm coming to you live from Sarasota, Florida, and I teach at the Pineview School, and my partner's Kristen from Frisco, Texas. We wanted to remind you that our AP Physics C E&M exam this year is going to be on May 11th. That's a Monday, and that will take place at 2 p.m. Eastern. That's where I live, but wherever you live, you're going to find out your time. And remember, you're going to have 2 questions. One's going to be 25 minutes, and then you'll have 5 minutes to upload. And one will be 15 minutes, and then you'll have 5 minutes to upload. Okay, so let's review a little bit from where we're come from. So we started reviewing for the AP exam last Monday, and we're still in the first section, which is electrostatics. And so we've been talking about charges in Coulomb's law, and we've been talking about the E field, okay? And so basically the force, Coulomb's law, and the E field are 2 big parts of electrostatics. And there's 2 more that we're going to get into tonight. And as I said, those 2 parts are potential and potential energy. So that's what we're doing tonight, potential, electric potential, and electric potential energy. Okay. Now, tonight, what we're going to do is we're going to be able to calculate the value of the electric potential from point charges. We're going to say what the electric potential is. We're going to give you a sense of it. And by the way, we're going to ramp up to this. This is going to take us a few days to really get a sense of what is electric potential. So we'll talk about this a lot, and as we go through the whole semester review, we're going to keep coming back to this concept of electric potential and what it is. I'm pretty sure by the end of the unit this semester, you will have a good sense of what it is. And also today we're going to do some math. We're going to represent the relationship between charge and difference in potential and work done. We're going to talk about work. We're going to calculate the electrostatic potential energy of a collection of 2 or more point charges. And we're going to calculate the amount of work needed to assemble some of these point charges. You're going to find some interesting problems here. All right, so we're going to start with electrical potential energy. Okay, and by the way, the symbol for that is U, capital U sub E, electrical potential energy. Okay, now you probably remember potential energy from your mechanics class, whenever you took it, that near the surface of the Earth, we have this gravitational field that points down G. And if you take a mass, M, and you put it in that potential, if you raise it at a certain height, then it has a potential energy, UG is equal to MGH. Okay. But we also know that work is equal to force times distance. And so that force is mg and that distance is h. So what we're showing is the amount of potential energy that we get is equal to the work we do to put that charge, to put that mass there. And we're going to do the same thing today, except not with masses and gravity, but with charges. All right. So this would be true whether this was electrical or gravitational. That is true of potential energy, although we're not going to do any calculus tonight. All right, so now this is our formula that we will use for electrical potential energy. By the way, this does equal to, when I integrate from infinity to r, f dot dr, that's what I get. And I'm not going to do the work with you, but I'm going to show you that what we would put in here is k qq over r squared dr. And when I did this work, I would get this answer over here. Now, let's talk about, though, not with the math so much, but let's talk about how we would solve a problem here. Okay, so we have two charges, okay, and they are 5 times 10 to the minus 9 each. That's each charge, and they are, sorry, okay, and those charges are 3 centimeters apart. So we want to know the potential energy of the system. All right, so let's go ahead and see what that looks like. So we're going to take this, we're going to imagine doing this problem. We're going to imagine that we start off with nothing in our universe. So I'm going to draw a line here, and I'm going to just, this is my own little private universe. That's the thing about being a physicist, is you can just draw a line on your whiteboard and you get your own little private universe here. So here's my little private universe, and I've got nothing in my universe, nothing. And I get to decide what I want to put in there. Now, I'm going to take a single charge. I'm going to take this charge of 5 nanocoulombs. Remember, there's nothing in my universe. And I'm going to put this 5 nanocoulomb charge in my universe right there. 5 nanocoulombs. And there it is. All right. And then what we're going to do is we're going to, I'm going to ask you, how much work did that take me? Did I have to do to bring that 5 nanocoulombs into this universe? And let's imagine that out near the edge of my universe, if we can talk about that, out near the edge of my universe, I made it appear here, and it was infinity away from this point, and I moved it here. Did I do any work? And the answer is no. Putting one charge in my universe, I can move it anywhere I want without doing work. And the reason that I don't do any work when I move this single charge around is because there are no other charges in my universe, and therefore no other forces. And so that means that it takes 0 work to bring my first charge in. However, now I'm going to bring in another charge. So I'm going to have another charge here, 5 nanocoulombs, and I just poof, there it is. It appears at the edge of my universe. And at first, it's infinity away from my first charge. And I'm going to move it from infinity over here. And now the distance between these two is 3 centimeters, or 0.03 meters. Now, how much work did I do to set this arrangement up, to arrange these charges? Well, to put the first charge in, 0 work. But to put the second charge in, the amount of work that I did is equal to the electrostatic, potential energy of my system. So this is K, Q, Q over R. And so what we have is we have 9, K is 9 e to the 9th. Okay, times, well, let's put that in, 9e to the 9th. And my 2 q's are 5e to the negative 9th, and I've got those squared. And then my distance is 0.03, okay? And so we have that, and put that in. And what we get is 7.5 times 10 to the minus 6, okay? Now, 7.5 times 10 to the minus 6, what? Well, this is energy. And so that means that the units for energy are joules. And so that's how much work I had to do to bring these two together. Remember, they're both positive, so they're pushing against each other, and I had to push them. And the amount that I pushed times the distance gives me that position. All right, so let's talk about this other thing called potential difference. Now, again, it's not my fault that we use this same word. We should call it something else, but we don't. So we really have to be clear. Are we talking about potential energy or potential difference? All right, now, we just said that in order to have potential energy, you need two charges. But in order to have potential, you only need one charge. Just like in order to have a field, you only need one charge. Potential energy is an interaction from two or more charges, or a charge and a field, but where did the first field come from? It came from a charge, so there's got to be more than one charges. However, if we only have one charge, we can still have a potential or a potential difference. All right, now, this is how they're related. And this is one of our golden formulas. And so as you get ready to take the test, we're going to show you, the ones that are the most important, but there it is. All right, now let's talk about potential difference. The potential difference is the difference in potential energy per unit charge between two places. All right, so here I have a point A, here's a point A, and here's a point B. And suppose I've got my UA and my UB. There's the potential energy I have here and the potential energy I have there. Well, what is the voltage? What is the potential difference between those two, AB? Well, that's going to be Q times delta U, okay? And I'm sorry, divided by delta U divided by Q, okay? And so that's how we're going to get that. That's how they're related. The units for volts are joules per coulomb, and I wish I could get you to remember that. That is so important, joules per coulomb. And then remember the potential difference between two places. It's a scalar field. It tells us how much energy I could extract or expend if I were to move that charge to that position from infinity. Now, this is going to make a little bit more sense when we look at this formula. This is the potential difference from a point charge compared to V0 at infinity. So what does that mean? All right, so imagine that I have a one-dimensional universe and I start out with no charges in my one-dimensional universe. And then at some point, well, I say, well, I'm going to put a positive charge here. Now, if I want to draw my potential, it's now no longer zero everywhere. My potential looks like this in this universe, in this one-dimensional universe. And the value of that potential, which is going to be V, remember the value, if this distance is R, V is equal to KQ over R, where that's my charge Q. Now, if I brought a negative charge into a universe and a positive charge, suppose I had, let's see, a positive charge here and a negative charge here, well, then my potential in my one-dimensional universe would look like this, okay? And it would then go like this, and we'd have a well, and then we'd have something like this. Now that's a one-dimensional universe, okay? I want to show you a two-dimensional universe. So let me pop over here to a simulation that I have for us today. And this is a simulation that someone made on GeoGebra. I think a man named, his name is Alan Olson. Thank you, Mr. Olson. And this is a really good simulation. I think you're going to like this as soon as my computer starts responding here. We're a little slow. Okay. Or not. Let's try that again. Okay. Okay, okay. I am having some tough points with this. I'm going to exit this page. Okay. And we're going to try and reload this. Just give us a second. Okay. All right, much better. Now, if you look at this situation, I'm going to show this to you like this. So we're looking at an XY axis. There are two charges that have been brought into this universe. Look at how they warp the universe. Look at that. My negative charge creates a well over here, and my positive charge creates this big hill. Now, we're going to talk more about those later as we get into, as we go through this and learn more about it. But, and in a few days, we'll talk about equal potential surfaces. But for now, we're going to send it over to Frisco, and Kristen is going to help us to understand some of these concepts with some really good problems. So, Kristen?
All right, so we are going to look first at 4-point charges and what happens if we have them in this arrangement, how they are here. So we have our 4-point charges. Each of them have a charge of positive Q. So I'm going to zoom in here, positive Q on each one. Okay, and the square has sides each of length A. So we want to know what is the potential energy of this arrangement of charges. Okay, so that would be the energy required to take them from infinity away to where they are now, right? So we want to look at what are the possible different arrangements we can look at, right? If the electric potential energy is equal to KQQ over R, well, we want to look at all these possible pairings of the Qs, right? So we could have this Q, the top left Q and the bottom left Q. We could have it with the bottom right Q or with the top right Q. I'm going to kind of make some different colors here so we can see them stick out. I could also have these two, and I could have these two. And let's see here. We could also have these other 2 corners here, right? So there are 1, 2, 3, 4, 5, 6 possible arrangements. But if we look at these, you want to look at the distances. So I've got the, and I really should have done, here, I'm going to recolor this real quick. I want to look at these outside 4 first. Why do I want to look at these outside 4 first? Because if the energy is KQQ over R, well, all four of these pairings have that same distance A between each of those charges. So if each one of these is KQQ over R, well, if the Q is the same, that becomes Q squared. The distance between them is A, then really I can say, well, of these 4, it's 4 times KQ squared over A. And then we also have those diagonals, right? So here and here. Now those will equal distance away, but that's not A. We've got to look at what that distance is, right? So then I also have plus these 2, which are K. It's still Q times Q, which is Q squared, but we got to look at what is that distance between them. So let's look at just that distance between them. So if this is our square, and this is A, and this is A, well, we know by Pythagorean theorem that this is the square root of 2 times A. So then this becomes over the square root of 2 times A. And so we can combine these together. We can pull out our KQ over A, and then this becomes KQ squared over A times, we're left with this 4 plus 2 over the square root of 2. Okay, so we want to look at those arrangements. We can look at each of those individual pairings to find what that total potential energy is of the arrangement. It's kind of the same thing when we had masses, right? When we had multiple masses and we were looking at, well, what is the gravitational, let's make another one here. What's the gravitational potential energy of those 3 masses, right? We had to look at the gravitational potential energy of all of those different possibilities of arrangements. We do the same thing here with the electric potential energy. Okay, and then what if we wanted to know what the electric potential was at the very center? Right, so these are still all positive Q. A on each side. So we want to know what the electric potential is. Well, the electric potential comes from each of the individual charges. So the electric potential V is KQ over R. Well, I've got a KQ over R to each one of these charges, right? So I've got from this point here to this charge here, that point charge is going to contribute to the electric potential at C. Charge 1, we'll call it. Charge 2 also contributes to the electric potential. Charge 3 and charge 4. All of them contribute to that potential at the center. And all of those charges are equal distance away. So really I can say, well, there's 4 KQ over Rs. So really we got to look at what that R is, right? Well, if we just said that the whole distance across here was equal to the square root of 2 times A, well, we're only looking from the center to one of these, so that's 2 of them. So that R would be the square root of 2 times A over 2. So then we can say this becomes 4 times KQ over R, which is the square root of 2 over 2 times A. So if we want to simplify that, we can bring that 2 up, and this becomes 8 KQ over the square root of 2 times A. Okay, so you're looking at that potential due to each one of those point charges in that arrangement. Okay, the next thing we can look at here is looking at the electric field and how we can determine which place in an electric field has a greater potential or a lower potential, what would happen to the energy to a charge, and the work on that charge in that field. So sometimes we like to look at and compare 2 different places in that electric field or in potential and look at that energy work. So here we have an electron that's placed in a uniform electric field at point A and is later found at point B, right? So the electron, I'm going to put a little negative here, is starting at position A, and then later on it's going to be at position B. So we want to know, is the work done on this electron positive or negative? And explain, is A or B at higher potential, or are they equal? And explain, and does the electron gain or lose potential energy? So I'm going to give you just a second here to think about that. Okay, so what do we think about the work done on the electron? Is that going to be positive or negative? Okay, well, we know, and this goes also back to gravity, springs, and in general, the definition of work and energy for those is that if we have a conservative force, right? A conservative force is anything associated with a potential energy, right? So when we're talking about spring force, gravitational force, anything associated with a potential energy is a conservative force. And then we can say in general that the work done is equal to the negative change in potential energy. So if we think about gravity, right? So when you are losing potential energy, gravity is doing positive work. And when you are gaining potential energy, then it's doing negative work. So if we look here and we look at our charge, if this is a negative charge, right? So we can think of also work being equal to the force over the displacement of our object. So here, if we look at it, which way is the force on this electron? Which way do electrons experience forces in an electric field? Is it with the field or the opposite direction of the field? Well, positive charges experience forces in the same direction, so negative charges experience electrostatic forces in the opposite direction. Okay, so if we look at the work here, then the work is going to be equal to the force times that displacement. And if our force is in the negative direction, then we can say that the work is negative. But since if we multiply it out also that the force is equal to Q times E, hold off on this part. If we look at the force and force is equal to Q times E, then we can say that this is equal to Q times E times D. Okay, so, but that negative charge, and we have, if we multiply that out, then we get negative Q times E times D. Okay, but is it going to gain or lose potential energy? Well, if work is equal to the negative change in energy, and if work is negative, then that means we are going to be gaining potential energy. Okay, and then is A at B or B at a higher potential? Well, we know those field lines always run from a higher to a lower potential, and so B would be at a lower potential. Okay, so we're going to toss it back to Roger over there in Florida.
Okay, thanks, Kristen. Well, so we're getting a sense of potential. Remember, there's a lot of invisible things we're talking about, so we're going to try and make sure that we can help you sort them out. Be patient. All right, let's go ahead and take a look at some other problems that'll hopefully help us to get the concept of potential down, and also to keep it, let's keep talking about potential, but also how is that different than potential energy? How's that different than the electric field? All these things that are related. So let's take a look. All right, so we actually did some of these from this very same problem a few nights ago when we were looking at the electric field. And so now we're going to revisit this problem. We're going to redo the electric field problems, but we're also going to add the potential. And so hopefully that'll get us a good sense of what we're talking about. So we've got the square of side A once again, and we've got these point charges. Here's Q plus in the lower left-hand corner. And here's 3 Q minuses in these 3 corners. So that's what we've got. Those are our 3 Q minuses and 1 Q plus. All right. And for those now, and also we have this point P, which is right here in the middle. All right. It says indicate with an arrow the direction of the net electric field at point P. So I'm going to, again, I did this last time. Let's label these 4 charges, capital A, capital B, capital C, and capital D. And let's talk about the electric field at P due to those 4 charges, A, B, C, and D. Well, I know that a charge Q means the electric field points towards it. And so I'm going to go ahead and point this electric field here, and I'm going to call that E sub A because that's the electric field due to charge A. Same thing with E sub B, we're pointing towards it, E sub B. Okay. E sub C, a negative charge, that means the electric field points towards it. And let's get in a little tighter here so we can see this a little bit better. And then E sub D, well, that's a positive charge, which means it has a field in this direction. And so that's going to be E sub D. And so if we looked at that, we can see that these two, E sub A and E sub C, are going to cancel. And what am I going to be left with? I'm going to be left with 2 of these. So if I can just find the value of one of them, since all these charges are the same, the magnitude, then I can go ahead and add those 2 together. Well, I know that the electric field from a single point from a single point charge is equal to KQ over R squared, where Q is the charge and R is the distance. So let's go ahead and look at this and see if we can get this distance. What is the distance from here to here? That's what we want to know. What is that distance? Okay. Well, if you look here, you can see that we've got a right triangle that's going to help us to find that distance. Since the side of my square is A, that means this distance from here to here is A over 2. And that means that this distance here, since this is a 45, 45, 90 right triangle, that's going to be the square root of 2A over 2. It's square root of 2 more than that. And so that means that what I have is I have 2 of KQ, and it's a capital Q, over the distance squared. And that distance is the square root of 2 over 2A squared. And so what we have now is we have 2KQ over, let's see, that's going to be 2 over 4A squared. And so that's going to be 2 in the top. And so what that gives us is 4KQ over A squared. All right, and that is our field at that point. That is our electric field at that point. All right, now that's something we did the other day. Now let's look and find, I'm sorry, I just found the magnitude of the electric field. So the work that is asked for down here, I did that up there. So we'll go ahead and say that's on the previous slide. Now, what is the electric potential at that point? Well, let's go ahead and, so the beauty of doing the electric potential, and this is what I love about teaching potential versus the electric field, it's a scalar, which means I do not have to add vectors. I don't have to worry about direction, and life gets a little bit easier. So, well, let's look and see. I know that the potential due to this Q plus and this Q minus, look, they're equidistant. Okay. And each one of those, one's going to be KQ over the distance, let's call it small r. And the other one is going to be K negative Q over small r. So when I add this one to this one, I get 0. And so these two cancel. And what we have are 2 of these. So I have 2 negative, and remember, V, the potential, is KQ over R. So that means that we have 2 times negative Q, forgot the K, over R. And the distance, again, is the square root of 2 over 2 times R. And so I've got 2 of those, and that's going to be 4 over the square root of 2 negative Q, K, and there's an A downstairs as well. I said R, I should have said A, which was correct. This is R. So that is the electric potential at the middle. Notice it is negative because I've got these 2 negative charges that do not cancel. And so that's my electrical potential. And what does that mean? Well, that means that if I start at infinity, okay, it means that the potential here is lower than it is at infinity. If I have a positive charge, it's going to roll in that direction. If I want to put a negative charge, I'm going to have to push it. All right. Now, it says a positive charge is placed at point Q. It is then moved, I think. Let's put a D there. It is then moved from point P to point R, which is the midpoint. So we start and we put a positive charge here, positive little q. I'm going to put a little q there. And we're going to move that. We're going to walk it down to here. Now, it doesn't say that I went in a straight line, and it doesn't have to, because as Kristen said, the electric force is a conservative force. So the path that we take is not important. The change is going to be the same. So the question is the work done by it, by the field, is it positive, negative, or 0? So let's kind of say what the field is doing. Now, if you remember, a few minutes ago, we said that the field was in this direction, okay? And so what would happen if I took this positive charge and I just let it go? I took this positive charge, here's the center, I know that this is the net field, E, and I let it go. What would it do? Well, hopefully what you're going to say is that it would accelerate in this direction. Now, of course, as it gets closer, the field is not uniform. It could change its acceleration, but right from there, we know in general, it wants to go in this direction. It wants to, if I let go of it, it's going to move in that direction. So if I have to move it in this direction, this is a positive charge, check it out. The force is in that direction, and my displacement is in the opposite direction. So the work done by the field, right, which is the one that's exerting a force, you can see that the field is anti-parallel, or the force is anti-parallel to the displacement. So work done by the electric field is the electric force, right, dotted with the displacement. That dot is cosine theta. So if these are about 180 degrees, or if they go in opposite directions, that means the cosine is more than 90, means the cosine is negative. So it means that the electric field has done negative work on this charge. Now, whoever pulled it, like if I'm the one who brought the charge, and if I grabbed it and I pulled it in this direction, then I do positive work, but the electric field does negative work. So that's very important that we make that distinction. All right. All right, let's move on. We got a couple more and then we'll call it a night. All right, it says describe one way to replace a single charge in this configuration that would make the electric field at the center of the square equal to 0 and justify your answer. All right, so here we have our box, and we want to know what can we do, just one charge, such that we're going to get rid of such that we will have no electric field. All right, and so when I look at this, well, I know that if I have symmetry, if I have a negative and a negative, those electric fields are going to cancel because those are in this direction. So those electric fields cancel due to symmetry. So if I could replace a single charge to create more symmetry, what I would do is I would get rid of this one, this positive charge, and I would make that a Q minus. And if I did that, I would have a minus, I would have an electric field in that direction, and the total electric field would be 0. So what I'm going to say is I would replace, all right, the bottom left with negative Q. The symmetry causes E equals 0 at the center. All right, so there we have that. Now, let's do this next one. We've got a, let's see, it says describe a single charge in this configuration that would make the electric potential at the center of the square 0. Well, potential is a scalar. So if we have 2 plus Q's and 2 minus Q's, and they're all equidistant from the center, that's going to do it. So I can replace any one Q minus Q with a single plus Q. Okay, if I do that, that means the sum of all the voltages is going to be equal to K negative 2KQ over, what did we say this was? This is, let's see, that's square root of 2 over 2A. And then we have a positive 2KQ over square root of 2 over 2A. And so this negative and this positive add to 0. And so I replace any one Q minus, either this one, or this one, with a Q plus, and I am good to go. All right. Now, let's go ahead and do one more, and then I think we'll get you out of here maybe in a minute or two early tonight. All right. Good for a Tuesday night. All right, here we go. Now, this one is a problem that we have to think a different way to do, different than the square. Why? It says 6 positive charges are set in a circle of radius r, so they equidistant apart as shown. Answer the following in terms of K, Q, and R. Write an expression for the electric field strength at the center of the circle. Well, I think that you could easily convince me that due to symmetry, that the E at the center of the circle is 0. Okay? Now, write an expression for the net amount of work that must be done to bring a 7th charge, Q plus, from a location far away to the center of the circle. Now let's talk about that. I've got a charge. It's very far away. It's a Q plus, right? And I'm going to bring it from here at infinity all the way, and I'm going to smack dab right there. That's where I want to put it. All right. So how much work do I have to do? Well, what I could do is I could figure out, let's see, how much, I could figure out how far it, let's see, I could figure out the difference in potential energy from here to here. However, it's much easier to find the amount of work by finding the change in potential energy. And so that's going to be delta V times Q. Now, what is the potential here at the center? Well, it's the sum of all of those KQ over R, and they're not vectors. So each one has a charge Q, and the distance is R, and there are 6 of them. So that is the potential at the center. What is the potential at infinity? It's 0. That is the definition, that at infinity, when we say conventional, at infinity, the potential is 0. But here in the middle, the potential is 6KQ over R. So what is delta U? Well, that's going to be delta V. So that's going to be delta V is 6KQ over R times Q, which is again Q. And so we get 6KQ squared over R. And if you think about it, hopefully that makes sense, because the first one we brought in, if we bring in the first one, it doesn't take any energy. So we then brought 1, 2, 3, 4, 5, 6 more. And that last one, that's how much energy it took, because I was working against all those 6. So that is how we would do that. Now, there's one more thing I want to show you before we go for the night. And that is the magic square of electrostatics. Now, I've taught this for many years, and this is just a mnemonic that helps me and helps my students to remember electrostatics. And so I always start in the top left-hand corner with the force. And the force is I'm so used to it. I know force from mechanics. And so we know that force is equal to K Q1 Q2 over R squared. That's called Coulomb's law. And the units for that are newtons. Okay. Now, if we take the force and we divide it by a charge, what we get is the E field, which is KQ over R squared. Notice I divided by Q to get from here to here. All right. Now, the units for this are newtons per Coulomb. Not too different from the units for a gravitational field, which are newtons per kilogram. This is newtons per Coulomb. All right, now we're going to talk about what over here, we're going to put U of E, which is, of course, potential energy. I'll go ahead and write that because that's new today. Potential energy. All right, and the potential energy is force times, usually when we get energy, work, we do force times distance. Well, if I multiply this by R, I get K Q1 Q2 over R. And so that is the formula for the potential energy for 2-point charges in a particular arrangement. The units for potential energy are joules. We learned that in mechanics. All right, now this is the other one. Remember, we're dividing by Q when we go here. So here we have the potential difference, and that's KQ over R. And the units here are joules per Coulomb because I divided by Q as I went down this way. Now, one more thing I want to show you, because we'll see this as we go this way. Another way to say the electric field, newtons per Coulomb, it has another set of units. And if we go to the right and we multiplied by distance, that means then we go to the left, we're going to divide. Okay, and we're going to divide by distance. And so what we get here are volts per meter. And so the electric field and units are either newtons per Coulomb or volts per meter. They're both. Okay, we'll probably visit this guy again because it's just really helpful. And it's kind of something I'm going to tell my students, hey, put this up on the wall when you're taking your AP exam on the 11th. So you see this in front of you. It'll help you to navigate back and forth. And of course, we can fill in a few. Not everything is done in here. We can say also we know that delta U is equal to Q delta V, right? Because this is, if we're dividing by Q here, we're multiplying by Q. And so you can see how this all helps us to find some relationships. Okay, so that's what I wanted to show you today. We decided that we wanted to give you a chance to find the electrical potential, okay? And also talk about the electrostatic potential energy. And these two are not the same thing. And we calculated the amount of work done to arrange a system of charges, and that is the potential energy of those charges. Okay, so that's where we are. Tomorrow night, we're going to we're going to keep looking at potential, and we're going to talk about something called an equal potential surface, which is a really cool way to look at a two-dimensional E field and potential field. Until then, keep working hard. We're really just so happy to see you here every night. Kristen, anything for our great students?
Nope, just can't wait to see you guys again tomorrow, same time.
Excellent. So once again, thanks for tuning in. We hope these are helpful, and we can't wait to see you Wednesday night, same place. Take care and have a good night.